Hi everyone, sorry for the hiatus these last couple of months. I've had a lot to do regarding college starting in a little bit, courses to sign up for, things to study, review, etc. And hopefully when I have courses starting, I can have some kind of consistent schedule with uploading or some topics that I'd like to pursue or follow up with on this channel, as well as just more time to, once my workload is at least through a significant amount, able to upload more and have certain topics in mind which I'd like to follow, especially as I'm taking these courses. Until then, I wanted to upload a couple of short videos, including this one, around some cool things or tidbits that I've seen in various kinds of math. And this one is one that I saw at a conference in May, and it's a proof that I'm probably never going to forget. It's kind of a toy version of a much more interesting and elaborate idea called the ping pong lemma in geometric group theory, which I won't get into here exactly, but the method of proof is similar. Geometric group theory has to do with studying groups via their actions on certain spaces and the geometry that results from it. And so this is sort of a small sampler of what happens when we are looking at a geometric or sort of small scale way of proving facts about groups or monoids of matrices. So it has to do with this pair of matrices in the group SL2Z, the special linear group, consisting of 2 by 2 matrices of determinant 1. So I'm going to write SL2Z is going to consist of all matrices A, B, C, D, where we have two conditions. So obviously because the coefficients are going to be in the integers, we have this, and the special linear part of it means that determinant, I should have called this something, I'll say capital A is equal to 1. Okay, so there's some intuition around this thing preserving a volume form, and this has a lot of other really nice properties. This is of interest in number theory in particular, but right now what I'd like to focus on is two special matrices. So we're going to let A equal this matrix 1, 1, 0, 1, and B, equal the matrix 1, 0, 1, 1, which is the transpose of A. Okay, and really what I want to show here is that A and B is a free monoid in SL2Z. And the proof is really cute. Okay, so what we mean by free is that there's no relations that hold between the elements in this monoid, everything that A and B generate. There are no non-trivial relations or things that sort of constrain the kinds of elements that we have. It's just matrices that are formed by products by treating A and B as letters, and we concatenate them like words using matrix multiplication. So what's our proof? Suppose, for the sake of contradiction, that a non-trivial relation exists. Okay, and a non-trivial relation is going to look like A to the M1, B to the M2, A to the M3, etc., is equal to B to the N1, A to the N2, B to the N3, etc. And notice that I've put powers of A on the left-hand side of this one, powers of B on the left-hand side of this one, this side. The reason why we can do this is because if we had both of these starting with some powers of A, without loss of generality, we could take B as well, then we could just look at whichever power of A is greater on the left-hand side, and we could cancel on the left. So we could just multiply by A to the whichever one is smaller, inverse, and we could make it so that we can reduce these the relation if we have two of the same letter at the front, cancel those out, and get a relation of the form a to the m1, etc., equals b to the n1 times something else. Okay, so we can always assume that this relation is of this kind of form. Now, from what we just showed, it can be written as AC equals BD for some elements C and D that lie in the monoid generated by A and B. Okay? And here we have C equals A to the m1 minus 1 times everything on this right-hand side, and D equals B to the n1 minus 1 times A and 2, etc. So this is going to be C and D in this relation. And yeah, otherwise we can cancel. Now we're going to look at the key part of what makes this geometric in nature, and that is a certain group action on the positive reals. So now SL2Z acts on the positive real numbers, which I'll put as R plus via fractional linear transformation. So I'll write this as FLTs. And the action is going to be that some matrix ABCD acts on X, or sometimes you can just write this as dot X or omit a symbol entirely. This is going to equal AX plus B divided by CX plus D. Right? So this is a group action. One can check that this is all good. One sends, the identity matrix sends X to X, so this is good. And we have the sort of associativity definition. This is a group action. So we have these matrices, right, of determinant 1, values in the integers, and 2 by 2. These are going to act on some positive real number X by sending it to this quotient over here. So this is a really important action in a lot of different kinds of math, especially number theory. And this is what we're going to analyze now. So we're going to denote by T and T prime respectively, where C and D send 1. Right? That is C is equal to, T is equal to C times 1, and then T prime is going to equal D times 1. So these are both going to be positive real numbers, as per the action above. Then we have A acts on T, right, as 1, 1, 0, 1 times T, which is going to equal, so AX plus B, right? This is going to be 1 times T plus T, which is going to be T plus 1. And this is going to be over 1, so this is just T plus 1. Great. Now B sends T prime to another number, right? Remember we defined B to be 1, 0, 1, 1. Sorry, times T prime. And as for the action again, we have T prime over T prime plus 1. Okay. Now we have to notice something really crucial here. No matter what T is in this one, right? No matter whatever the action is of C on 1, we always know that A is going to send an arbitrary positive T to T plus 1. Because this group action is going to be in the positive reals, we know that T plus 1 is greater than 1. However, if we have this positive real number T prime and we're dividing by something slightly greater than it, T prime plus 1, then this is necessarily going to be less than 1. So what does this mean, right? Because we've acted on T by C first and then A, and then on T prime by D first and then B, we've really acted on T and T prime respectively by the full force of the non-trivial relation on both sides that we purported to exist. That is, AC sends 1 to something less than 1, but BD sends 1, to be something greater than, I mixed this up. This is going to be greater than 1, and this is going to be less than 1. Okay? Hence, no relation can exist that is AB and SL2Z is free. And we're done just by looking at where this action sends 1 on both sides. Thanks for watching.